In this lesson, I'll show you how to solve an electrical problem by the Laplace transform. This is question number 4. Specifically in this question, we'll look at an RL circuit with AC source. The question reads, a switch is closed at time is equal to 0 when the applied voltage is 0 and increasing. Find the current. First, let's start with Kirchhoff's law. Kirchhoff's law states that the sum of the voltage that drops across a resistor, an inductor, and a capacitor in an electrical circuit must be the same as the voltage source applied to the RLC circuit. So with that said, we have this expression representing our electricity source, which is 80 times sine 400t, and this is equal to the voltage drop here, which is the resistance times the current. And that's the instantaneous current. So we have R times I plus the voltage drop here, which is represented as L times di over dt, the rate of change of current with respect to time. Let's go ahead and replace this R with 4 ohms. We have 4 times I plus the inductance here is 0.02 henries. And instead of writing di over dt, since we're using the Laplace transform, I'll use a format which is more applicable to this technique, which is I prime, and the left side stays the way it is. Next, I'll take the Laplace transform of each term. So I'll take the Laplace transform of this term. This gives me 80 times the Laplace transform of sine 400t. Taking the Laplace transform here gives me 4 times the transform of I. And the Laplace transform here, for that, we'll need to use this relationship where the transform of the first derivative is equal to this expression. So I have plus 0.02 times s, the Laplace transform of f of t, which in our case will be simply the Laplace transform of I, minus I at time 0. The current at time 0 is equal to 0. So I won't write down anything beside this term. Now I'll isolate for the Laplace transform of I, and I need to find out what this is equal to at the same time. Shown here, we have the Laplace transform of sine at is equal to this frequency function. Our a value here is 400, so I'll have 80 times 400 over s squared plus 400 squared. In the step to come, I'll multiply this by 400. This is equal to, and I'll factor out the Laplace transform of I. We have this times 4 plus 0.02 times s. My goal is to isolate for this, the Laplace transform of I. So I'll divide both sides by 4 plus 0.02 s. Firstly, 80 times 400 is 32,000. Over s squared plus 400 to the power of 2 is equal to 16,000. Having divided the right side by this expression, you need to place it here too. 4 plus 0.02 s is equal to the Laplace transform of I. Now interestingly, if I factor out 0.02 from this binomial, what will happen is this will go away, and 4 divided by 0.02 gives us 200. So this becomes 200. And having factored it out, it actually becomes a factor in the denominator. So 32,000 divided by that, 32,000 divided by 0.02 gives us 1.6 million. So I'll write that down. 1.6 million at the top, divided by the expression at the bottom, which is s squared plus 16,000, that binomial times 200 plus s. And this is equal to the Laplace transform of I. Now, this expression that you see on the left doesn't match any known Laplace transform that we used in the table in previous videos of this series. So what we have to do is use a method for separating this expression into partial fractions as a rational fraction that has quadratic factors in the denominator. If we can do that, then we can possibly match it with a known Laplace transform. That being said, let's go ahead and do that. I'm going to separate this into partial fractions. Notice that this right here is a quadratic. And when you have a quadratic as a factor, you have to introduce two unknowns, a and b. And technically, since we're dealing with s, it should be a times s plus b over this factor. This right here is a linear factor, so you only introduce one unknown, which I'll call c. This is equal to this side. Next, what I'll do is find a common denominator between these two terms. I'll cross multiply. This gives me 200 plus s times as plus b. This multiplied to c gives me c times s squared plus 16,000. And if I find a common denominator here, it will actually model this. So instead of showing you this step, I'll just clear the denominators, leaving me with 1.6 million on the right side. Then you would have to simplify, equate the coefficients, and find out what a, b, and c are simultaneously. Think of it as a linear equation. And we've done many of these videos in the past where we use partial fractions. So I'm going to fast forward a little bit and tell you what a, b, and c is equal to, but feel free to watch one of our other videos where I show you how to undergo partial fraction expansion. Your a value should equal to -8. Your b value should equal to 1,600. And your c value should equal to 8. So you have to take these numbers and substitute them into here, here, and here. Let's go ahead and do that. Now, unsurprisingly, this and this will match functions with known Laplace transforms. And I've written them down over here for reference. Take a look. If we have a over s squared plus a squared, let's see if we have that here. We sort of don't, but if you look at this specifically, we have 1,600 over s squared plus, this can be changed into 400 to the power of 2. Similarly, this can be changed into 400 times 4. Let's go back. That is equal to sine at. So 4 times sine, our a value here has to be 400 times t. Next, you'll do it again with the following. Let's see if that matches any of the ones that I have up here. It does. We have s over s squared plus a squared. So if I write this as -8 and s at the top, s squared plus 400 squared. Once again, my a value is 400, and I can write this as cosine at. So I have -8 cosine 400 t. This term plus this term, and we have to do this one more time for this term. Let's see if that models one of the ones that I have in the reference. It does. 1 over s minus a. This is s plus 200 technically, but we can write the denominator down as s minus -200. And we can pretend that this 8 is a factor being multiplied to 1. If we do that, that gives us e to the power of at plus e to the power of, my a term here has to be -200 times t and the factor 8. Putting this all together, we get is equal to the Laplace transform of I. And technically, this should just read I, the current. You can go further and combine these two terms. And we've done this in the past. I do have a video where you can combine sine waves with cosine waves. And if you do that correctly, you should end up with your final function as I is equal to 8.94 times sine of the angle 400t minus 1.107 plus 8 times e to the power of -200 t is equal to I. Now, if you're confused by this part, how I combine this into the following, feel free to use the formulas that I've provided here, which technically tells you how to go from sine and cosine as a sum into a sine wave. And there you have it. That is how to solve electrical problems by the Laplace transform.